So in this video, we're going to give an equivalent condition for a set being definable. And the way that this is going to go is that we're going to build up this collection of, it's really going to be a collection of collections of sets. That's very confusing. But each one of these, each dn, you should read as a collection of definable sets, right? So each element of dn is going to be a set. So if we pick, I don't know, say x in dn, x will be a set. It'll be a definable set if we set things up the right way. And the n is going to signify the length of the tuples that are in X, right? So dn is a collection of definable sets, each one having tuples of length n. Now, I'm telling you that, obviously this is not a rigorous proof, I'm just trying to communicate the sort of intuitive meaning behind this, and then we'll get into the proof later. But that's how you should think about and regard dn. And so, of course, each element of dn will be a subset of m to the n, because, of course, those are just tuples of length n. And then we take the smallest collection satisfying certain properties that will guarantee that we're talking about definable sets. We require that it be the smallest set satisfying these properties, so that once we establish that the definable set, anything that has these properties are definable, then we take the smallest such set, ensuring that nothing else, right, no non-definable things get into this collection D. So just to kind of give a little bit of explanation and intuition, at least for a small handful of these rules, this rule or property or requirement that m to the n is in dn, well, for any tuple of length n, we can define the set of all of those tuples with a fairly simple, formula that just makes a whole bunch of equations, basically. For instance, if I wanted to get the set of all pairs, then I could say, take my formula phi of, let's make it phi of v1, v2, to be the sentence, so I should say is to not confuse it with the equal symbol in the language, v1 equals v1, conjunction v2 equals v2, and in fact every pair will satisfy this formula and therefore be definable, and therefore we would like to have the set of all pairs in D sub 2, and likewise for any other integer. So that's why we have this clause here, is that it's easy to understand that that the set of all tuples of length n is always going to be a definable set of tuples and should get into D sub n. So similarly, right, we can come up with simple, easy formulas that define the graph of a function, the graph, so to speak, of a relation. I think I somehow accidentally erased a little bit there, but and likewise, right? And particularly with some of these that it might not be completely transparent what they're doing here, I think in the process of the proof it'll become more apparent how these capture needed definable sets. So, okay, with that set up out of the way, I'll just jump into the proof, right? So we are going to prove that if a given set is definable by some phi, then it satisfies these properties. So to do so, we suppose that phi defines x, and we will prove by complexity, induction on the complexity of phi, that x is in one of these D sub n's. In particular, it should likely